we have covered the dissolved oxygen dynamics. The dissolved oxygen dynamics in the seas are important because the lack of dissolved oxygen will cause hypoxia, and hypoxia is stressful to marine organisms. So if you look at the equations for respiration and photosynthesis, the production or consumption of oxygen is connected to the consumption and production of CO2, carbon dioxide. Therefore, the CO2 and oxygen are intricately linked in the seas. Okay. So in my lab, we focus more on the measurement of dissolved oxygen, partly because it's easier to measure. Okay, dissolved CO2 is harder to calibrate and harder to standardize. However, because of the climate change problem with the souring of the seas, there is a global network that is actually measuring acidification in the seas, focusing on the CO2, alkalinity, and the partial pressure of CO2 in the seas. So when CO2 is dissolved in the seas, it forms carbonic acid, which will dissociate into bicarbonate and carbonates. Okay. So this is essentially the buffering system of the sea. Okay, and this is what makes the sea a major sink of CO2. So as I've mentioned earlier, the ocean now is known to absorb up to 50% of the anthropogenic emission of CO2. So this is an important system that allows the sea to absorb the CO2. Of course, there are other greenhouse gases, for example, methane, nitrous oxide, CFCs, chlorofluorocarbons, and ozone. Okay. However, as I mentioned, also based on the global warming potential (GWP), CO2 is the most important because of the amount of CO2 that's being produced. Okay. So long-term analysis have shown atmospheric CO2 is increasing and the pH of the sea is decreasing. So there is a definite decrease in the pH of the sea throughout the world. Okay, so these have consequences, especially towards marine organisms that produce carbonate shells. The main one that comes to mind is, of course, your coral reef systems. You also have some other organisms, for example, the theropods, that also require carbonate for their shells. So these are being affected by the decreasing pH in the seas, by the souring of the seas. So there is a definite link to the scientists have been able to link the souring of the seas to detrimental effects on coral reefs and also on carbonate shell organisms. So how is CO2 transferred in water columns. So we have three different pumps. We can divide the transfer of CO2 in water columns into three different pumps: solubility pump, physical pump, and biological pump. The gas exchange with the atmosphere, because we have CO2 in the atmosphere, so there is solubilization. Okay. Of course, we have already learned that the solubility of gases in the sea is inversely related to temperature, salinity, okay, and also CO2. Okay, so what does this mean? This means that when the temperature is high here, the solubility of CO2 decreases. Salinity is high here, solubility of CO2 decreases. And when the concentration of CO2 is high here, the solubility of CO2 also decreases. Okay. But what affects the concentration of CO2? So for the last part, what do you think affects the concentration of CO2 in the seas? So mainly related to two processes. One will be, of course, your photosynthesis. So photosynthesis will fix CO2 and release oxygen. The other is, of course, respiration, which will absorb CO2 and absorb oxygen and release CO2. So this is essentially the opposite of the dissolved oxygen dynamics that we have learned. Okay, but now we are focusing on the CO2. So the first pump is solubility pump, where the CO2 from the atmosphere enters the sea. The second pump is the physical pump. Physical pump essentially means the thorough mixing of the water column. Okay, thorough mixing as opposed to the formation of stratification in thermoclines and haloclines. So this is in opposites. Okay. When you have stratification, you do not have mixing. Okay, you have stratified layers of water. Okay, for the mixing pump to work, you have to have thorough mixing. For the physical pump to work, you have to have thorough mixing, and this usually occurs when the waters are very rough, winds are very strong, usually in winters, usually during monsoons. So what this do is this will bring down whatever CO2 is here, and then the reduction of CO2 here will increase the solubility also. Okay, so the physical pump, thorough mixing of the water column that ensures the CO2 is transferred throughout the water column. Then the last pump is the biological pump. For biological pump, it is related to biological processes. So initially, is the CO2 is fixed by your phytoplankton. Okay. So when it is fixed by your phytoplankton, it enters the biomass of the phytoplankton. And phytoplankton at the end of its life cycle dies and sinks. And this sinking forms the biological pump where the CO2 is transferred from the surface to the bottom, but in the form of phytoplankton biomass. Okay, so this is uh, how a biological pump works. So this is where the CO2 is incorporated into phytoplankton biomass. CO2 can also be incorporated as a calcium carbonate shell, which also at the end of the life cycle of the organism will also sink. So this is a carbonate, is also a biological pump, but in the form of a carbonate incorporation. So these are the biological pumps at work. You have a physical pump, and you have solubility pump. So these are channels how the CO2 from the atmosphere can be transferred to the surface area and then throughout the water column. We'll continue. So the transfer of CO2 in water columns is through solubility pump, physical pump, biological pump. So for biological pump, we have both organic carbon and carbonate forms, as I mentioned. So the organic carbon form is the one that is incorporated by the phytoplankton. And for the physical pump, it's thorough mixing. Also, at certain areas of the ocean, you have downwelling, where the CO2 in the surface waters can be transferred into the deeper waters. So why is the information about CO2 transfer important? Because this has been suggested as solutions for the global warming problem. So the idea is, if we can increase photosynthesis, we can stimulate the CO2 fixation, and then the fixed CO2 can be drawn or transferred into the deep water reservoirs. So if you have learned, the Great Ocean Conveyor Belt, once the water is brought into the deeper layers, it remains there for 1,000 years. So, uh, so you are postponing the problem. You are able to uh, so, reduce the impending climate change problem, okay, or postpone it to a later time by uh, drawing down the CO2 from the atmosphere into deep waters. So you are able to essentially postpone it. Okay, doesn't solve the problem, but you have more time to tackle the climate change problem. Okay, you have more time. It gives you more time if you're able to draw down the CO2. Okay, however, later we'll see uh, how it is actually being proposed. Okay, so solubility is related to inversely related to temperature, salinity, and CO2. And because the CO2 is related to photosynthesis and respiration, so inevitably it is also related to biological processes. So the physical pump is related to monsoons and winters, especially for temperate countries. And for biological pump is related to photosynthesis and respiration. Okay. So we've seen this equation. So it's actually a reversible equation where the CO2 dissolution of CO2 in the seas form carbonic acid, bicarbonates, and carbonates. So if you look at this, you'll see that the percentage of hydrogen being formed is higher than carbonates. So at the end, pH will reduce and there will be acidification because of this protons being formed. And because more protons are being formed than the carbonates, with pH, with the souring of the seas, the equation is actually being driven towards the other side. So what it means is it is harder to produce carbonates because the equation is being driven towards the other side. So with souring, with acidification, this equation is driven towards the other side. It's harder to form carbonates. So organisms that require carbonates to build their shells, to build the reef systems, will have to expend more energy to incorporate carbonate into their body. Okay, so the organisms have to use more energy, and it will be more stressful conditions for them. So there are two forms of calcium carbonate, calcite and aragonite. So aragonite is the more favorable form that is favored by organisms. So in chemistry, marine chemistry, they use the omega or saturation state to determine the thermodynamic tendency for calcium carbonate to form or dissolve. So this omega for aragonite, if it's more than 1, okay, so it is favorable for calcification. However, if it's less than 1, there's undersaturation, so it favors dissolution. So if you look at the equation for saturation state, it is dependent upon the carbonate ions. So if you looked at the equation here, because of acidification and because it is driven towards the other side, there will be less of this. So your saturation state will tend to move towards less than 1. So there will be undersaturation and it will favor dissolution of the either coral reef systems or other carbonate shell organisms. Okay, so this is why the acidification or souring of the seas will not be good for the organisms that require carbonate as their shell or as their skeleton.